I was in a coffee shop this morning, and it just hit me. Humans are, without a doubt, the chattiest species on the planet.
Okay.
I mean, it is just constant.
Oh, absolutely.
We're sending signals, waving, making all these noises. My coffee's ready. Watch out. Did you see that email? It feels so effortless.
With us, yeah.
But the source material we're looking at today really drives home that if you try to get a computer to understand that same stream of noise, it is an absolute chaotic mess.
It's a nightmare for a machine.
Yeah.
To a computer, natural language isn't, this beautiful thing. It's a stream of noisy data, full of gaps and contradictions and things that just don't make logical sense.
So that's our mission for this deep dive. We are unpacking the fundamental science of natural language for communication.
Yeah.
And just to be clear, we're not just talking about how to build a better chatbot that, resets your password.
No, this is much deeper. We're going to trace the whole history of how we moved from those early days where programmers literally tried to handwrite every single grammar rule, all the way to the modern era, where it's all about statistical best guesses that power things like translation and speech recognition.
And we have some truly bizarre examples to get through today. I'm talking Wumpus monsters, ham sandwiches that want a beer.
Oh, the ham sandwich. A classic.
And why speech recognition software thinks everyone's talking about the beach.
Recognize beach.
Recognize beach. But before we get to that, we have to start with the rules. The source material, chapter 23, it lays this out pretty clearly. Communication is the intentional exchange of signs.
Right. And for a machine to process those signs, it can't just, rely on intuition. It needs structure. It needs a grammar.
Okay, this is where I hit my first wall reading this. If you want a computer to speak English, why can't you just give it a list of every possible sentence? I mean, hard drives are huge now. Just list them all.
That would be the dream, wouldn't it? It would be so simple. But you immediately hit this wall called data sparsity.
Data sparsity. Okay, break that down for me.
Yeah. Well, think about it like this. Let's say you have a vocabulary of just 100,000 words. Seems manageable, right?
Yeah, that seems doable.
But if you want to calculate the probability of just a 3-word phrase using those words, you're looking at a quadrillion possible combinations.
A quadrillion.
A quadrillion.
Okay, that's a lot more than I thought.
Exactly. So even if you had a database with 1,000,000,000,000 words of text, you would not even scratch the surface. Most perfectly valid sentences have never been said before in human history.
So you can't list them. You have to generalize.
You have to find the patterns, exactly. Like in English, we have a pattern. Black dog, adjective, noun. But you look at French, and the pattern is usually the other way around. Chien noir.
Right, so we create these categories, noun, verb, adjective, and we write rules for how to string them together. And this is what the text calls phrase structure grammars.
Correct. But here's the catch. Not all grammars are created equal. There's this hierarchy of complexity. It's known as the Chomsky hierarchy.
I remember this. It's like a ladder, right?
A ladder of expressive power, yeah. At the very bottom, you have regular grammars. They're very simple, good for patterns, like A always comes after B.
But I'm guessing that's too simple for human speech.
Way too simple. It can't handle nesting. You know when we say something like, the cat that the dog chased ran away?
Right, the parentheses.
Regular grammars just break. They lose count as soon as you put parentheses inside other parentheses.
So we climb the ladder. Next up is context-free grammars, or CFGs.
Yep, and this is the bread and butter of computer science. Most programming languages, like Python or Java, they're defined by these CFGs. The rule is just rewrite A as B, and it doesn't matter what's around it.
But English is all about context.
Exactly. Context matters. So at the very, very top of the ladder, you have things like recursively enumerable grammars. These are the heavy hitters. They're basically Turing machines.
So why don't we just use those for everything? If they're the most powerful, why not use them for AI?
It's a trade-off. The higher you go on that ladder, the more computationally expensive it gets. I mean, you could use one for a chatbot, but it might take a week to figure out what hello means.
Okay. Efficiency versus power. So to see this in action, the source uses this really stripped-down language called E0. And it's for AI agents in a Wumpus world.
Ah, the Wumpus world, a classic AI test bed. Imagine a grid, a monster, some pits you can fall into.
So in this world, this E0 grammar, it generates sentences like, The wumpus is in 2 too.
Yeah, logical.
Very logical. But the text points out that even this super simple grammar has a huge flaw.
It's the Goldilocks problem. It's never just right.
Okay.
First, the grammar overgenerates. The rules are simple, noun phrase, then verb phrase. But without more rules, it just spits out nonsense like, me go Boston.
Me go Boston.
Or I smell Pitt's Pompous John. It follows the syntax rules. But it's garbage.
And on the other hand, it undergenerates.
Exactly. It might reject a perfectly good sentence like, I think the wumpus is smelly, just because the rigid rules didn't have a slot for, opinions.
So we have the rules, we have the words. The next challenge is making them fit together. That's parsing.
That's parsing, yeah. It's about finding that hidden structure, turning a flat string of words into a tree diagram that shows how everything is related.
But there's a trap here. The text makes a big deal about this. The ambiguity trap.
Oh, this is the bane of every computer scientist's existence. Let me give you the example from the text. Imagine a parser reading this sentence. Have the students in Section 2 of Computer Science 101 take the exam.
Okay, sounds like a command, like make them take the exam.
Now compare it to this. Have the students in Section 2 of Computer Science 101 taken the exam.
Oh, I see. The first 10 words are completely identical.
Exactly. So a parser reading from left to right has to guess. Is have a command or is it the start of a question? It has no idea until it hits that 11th word.
And if it guesses wrong.
It has to throw away all that work and backtrack all the way to the beginning.
That sounds incredibly slow. You'd never finish a paragraph.
It is exponentially slow. The solution is a technique called dynamic programming, specifically the CYK algorithm.
This is the chart parser idea.
Yes, and it's actually a very human insight. Once you figure out that the students in Section 2 is a noun phrase,
Right.
you shouldn't have to figure that out ever again. You just save that result in a chart. It's like a database of partial solutions.
So you never reanalyze the same chunk twice.
Precisely. The CYK algorithm, it takes a grammar in this special format, Chomsky normal form, and it can parse any sentence in what we call O(n)(3) time.
Meaning if the sentence gets longer, the time goes up, but it doesn't just, explode into infinity.
Exactly. It makes parsing manageable.
But manageable wasn't enough, was it? Because around the 90s, there was this huge shift. We stopped asking, is this sentence valid?
And we started asking, how probable is this sentence?
This is the rise of probabilistic context-free grammars, or PCFGs.
And this changed everything. Instead of just dry rules, every single rule gets a probability score.
And you don't just guess the scores. You learn them from data.
Right. The text mentions the Penn Tree Bank. It's this famous data set, 3 million words from the Wall Street Journal, where actual humans went in and painstakingly drew out all the parse trees.
So the computer looks at that and says, okay, 80% of the time, a noun phrase is just article noun. And only 20% of the time, it's just a noun on its own.
Exactly. It learns what's likely. But even PCFGs had this blind spot. The text calls it the banana versus bandana problem.
I loved this example.
Yeah.
It really highlights how, dumb a computer can be.
So a standard PCFG is context-free. It knows the probability of eat being a verb, and it knows the probability of banana being a noun.
And bandana being a noun.
Right. But it doesn't track the relationship between them. To the grammar, eat a banana and eat a bandana are structurally identical. Verb, article, noun.
But it has no idea that one is food and the other is clothing.
It has no clue. So, unless you're a goat, eat a bandana is pretty unlikely.
Right.
To fix this, we created lexicalized PCFGs. We basically augment the grammar with what we call head words.
Head words.
It just means we don't just look at the category verb. We look at the specific verb eat. And we see that eat has a really strong statistical relationship with the noun banana, but almost zero relationship with bandana.
So the rule becomes something like verb eat is followed by noun banana.
Yes. Now, the probability depends on the specific words, not just the abstract categories. And that connects the structure of the sentence to the actual meaning of the words.
And speaking of meaning,
Yeah.
that's the ultimate goal, right? We don't just want pretty trees, we want to know what's actually being said.
Which brings us into the domain of semantics.
The text mentions compositional semantics. It sounds complicated, but it's basically like math, right? 3 + 4 = 7.
Pretty much. If you know what John means, and you know what loves means, you can translate John loves Mary into a logical formula. Loves John, Mary.
But human language is just so slippery. The text brings up tense. John loved Mary.
Right. Now you suddenly need this whole other thing called event calculus.
Wow.
You have to map that event relative to time. Love means the event happened after the beginning of time, but before right now.
And then there's quantification. This one kind of blew my mind. The sentence, every agent feels a breeze.
Oh, the classic Stope ambiguity. Think about it. Does every agent feel the same breeze?
Like one giant fan.
Exactly. Or does every agent feel their own personal breeze? The grammar has to be able to represent both possibilities.
And we haven't even touched on pragmatics yet. Indexicals.
Words like I, here, and today,
Right.
their meaning is completely empty without the specific situation. If I say I am here, it's true. If you say it, it's true. But I and here refer to totally different things.
The machine has to know who is talking and where they are.
To get any truth from it, yeah.
You know, the part I found most entertaining was the real-world ambiguity. Newspaper headlines are apparently a gold mine for parser errors.
Oh, they're the best. Headlines cut out all the little glue words to save space, and it just creates havoc.
Squad helps dog bite victim.
Right. Did the squad help the victim, or did the squad, help the dog do the biting? Syntactically, both are possible.
Or hospitals are sued by 7-foot doctors.
Are the doctors 7 feet tall, or are they podiatrists?
Right.
Foot doctors.
These are funny to us, but for a machine, they're just nightmares.
Yeah.
And then there's metonymy, the figurative speech problem. The example is, the ham sandwich on table 4 wants another beer.
This is such a profound problem for AI. A strict logical grammar looks at that and just short circuits. Sandwich is an inanimate object. Inanimate objects can't want beer, therefore the sentence is false.
But any human waiter knows exactly what that means. It's the customer with a yum sandwich.
Exactly. To handle this, the grammar needs a metonymy relation. It has to understand that one object can stand in for another related object.
So how does a system actually decide what you mean?
It's a combination. Disambiguation needs like 4 different models working together. You need a world model, do the sandwiches, drink beer. A mental model, what's the speaker's intent? A language model, and then an acoustic model.
It's amazing we can communicate it all.
It really is a small miracle.
So let's look at 2 huge success stories where this statistical approach really did conquer the world. Translation and speech recognition. Machine translation has had a roller coaster history.
A huge roller coaster, yeah. It started with so much optimism back in 1947. Warren Weaver famously said something like, look, Russian is just English coded in strange symbols. We just need to decode it.
It's like code breaking.
Exactly, like cryptography. But then, reality and nuance set in. In 1966, the famous Ayla Pack report basically said it was hopeless and funding just crashed for decades.
But it came back with statistical power. The text uses the Vauquois triangle to visualize this.
Right, imagine a triangle. At the very top is this idea of the interlingua, a perfect universal concept of meaning. The idea was you'd translate English to this universal concept, then from there to French.
That sounds impossibly hard. You'd have to model the whole universe.
It is. It's incredibly hard. So we usually cheat. We go lower down the triangle. We use a transfer method mapping English grammar directly to French grammar. Or, even simpler, the statistical solution where we don't try to understand grammar at all. We just count things.
The noisy channel model.
Right, and this is a bit counterintuitive. We treat French as if it were just corrupted English.
Corrupted.
Yeah, we assume the speaker meant to say something in English, but it passed through a noisy channel and came out as French. Our job is just to decode it back to the original English.
That feels completely backwards, but it works.
It works surprisingly well. You need 2 things. A translation model, which tells you that the word chien probably means dog, and a language model, which tells you that black dog is a valid English phrase.
And the text breaks this into 3 steps. First, break the sentence into phrases. Second, translate those phrases using a database.
And that database comes from these huge bilingual texts like the Hansards, which are Canadian parliamentary debates published in both English and French. Millions of matched sentences.
And third, this is the tricky part, distortion. Reordering the phrases.
Because word order is different. English says smelly wumpus. French says wumpus malodorant. So you have to calculate the probability of moving a word around.
The evaluation example they gave with Google Translate in Danish was really interesting.
Yes, it translated the Danish phrase for regularly cited, as frequently mentioned.
Which technically isn't a literal translation.
Technically not, but the meaning is perfect. And that's the victory of the statistical approach. It communicates the idea even if it's not word for word.
Okay, let's switch to the final frontier. Speech recognition, or as the text calls it, solving rec-a-nice speech.
Recognize speech, recognize speech. Say them fast enough and they sound almost identical.
This gets into the messy physical reality of sound, co-articulation.
Right. We don't speak in neat little blocks. The S sound in nice physically blends into the B in beach. Your mouth is already moving to the next shape before it finishes the current one.
So how does a computer even begin to break down that continuous slur of sound?
It just slices time into tiny, tiny chunks. We call them frames, usually about 10 milliseconds long.
And for each frame, it extracts the key features.
MFCCs, mel-frequency cepstral coefficients. It's like a digital fingerprint of the sound energy in that split second.
But we aren't listening for words, we're listening for phones.
Phones are the building blocks of sound, right? And phonemes are the units of meaning within a language.
The text uses the example of the HMM, the hidden Markov model. That seems to be the engine under the hood for all of this.
It is, and HMM sees a phone as a little state machine. There's an onset, a middle, and an end. It knows a T sound starts silent, has a burst of air, and then ends with a hiss.
And it has to handle dialects. The tomato model.
Tomato. The pronunciation model has to have paths for both. If you only program for tomato, you're locking out half the English-speaking world.
So to finally solve recognize speech, you're combining three things.
Yes. You have the acoustic model, which asks, what does this sound match? Then the pronunciation model, what sounds make up words? And finally, the language model, which asks, how likely is the sequence recognize speech versus recognize speech?
And recognize speech usually wins the probability war.
Usually. Unless you're actually talking about vandalism at the seaside, the computer just rolls the dice on all the possibilities and picks the one that's statistically most probable.
You know, this highlights the biggest shift in this whole field that we've covered today.
What's that?
We moved from knowledge engineering, where we tried to be smart and write down every single grammar rule by hand,
Right.
to machine learning.
We just stopped trying to teach the computer definitions. We stopped trying to be the expert telling the machine how English is supposed to work.
And instead, we just started exposing it to massive amounts of data in the wild.
What?
The web, phone transcripts, parliamentary records.
And that's the big takeaway. The best results don't come from the cleanest, most perfect rules. They come from the messiest data. We let the data teach the machine the patterns.
But here's a thought to leave everyone with. If these systems are just using n-gram statistics and noisy channel guesses to predict the next word, do they actually understand us?
That is the big question, isn't it?
Or are they just really, really good at predicting the next token?
I think if you go back to the ham sandwich example, you see the cracks. They can predict that beer often comes after sandwich in that context, but can they reason why? Can they visualize the customer? That, I think, is the difference between processing and actually understanding.
Next time you're in a conversation, try to notice the ambiguities. Notice how your brain effortlessly solves problems that make a supercomputer sweat. Thanks for listening to this deep dive.
See you next time.